for the participants Indonesia and from Australia. Good day for the participant in Tanzania and Zambia, and then good morning for you, Professor Jerome. Thank you so much for attending this webinar, and also it's our pleasure to have Jerome with us to share about the Bayesian statistics and overview of current recommendation. So let me introduce myself. My name is Mila Tejamaya. I am the current president of Indonesian Industrial Hygiene Association. Very nice to see everyone tonight. Okay, so without further ado, Jerome, time is yours.
Thank you. So good day, good morning, good evening, everyone. Thank you for taking the time to listening to me. And again, I'm very thankful to be able to speak to you. So I'll start my slideshow for today. All right. Sharing screen. Okay, so you should all see my slideshow.
Yes, it's clear.
Okay, excellent. So yesterday we talked about exposure variability. We explained there was a statistical model to be able to deal with the fact that we measure only a small proportion of what we need to make a decision about, the log normal distribution. We also learned how we can estimate the uncertainty associated with this need to extrapolate from a few measurements to a larger population of interest to us, and how, what recommendations were existing for how to interpret traditional confidence limits and the confidence intervals to decide whether the situation was a needed action or was acceptable. So today I'll try to explain a little bit, to give a little insight about a part of statistics that's somewhat recent, but fairly widespread in our field, thanks to the existence of several practical tools almost now for more than 10 years. So I'll try to explain a little bit about Bayesian statistics and why they are so helpful, and we'll see how they can be helpful. And the end of the morning will be I'll try to make a short summary about some key elements of some current recommendations for sampling strategies and data interpretation procedures or schemes. And tomorrow would be more practical. So try to do as yesterday, taking a break in a bit less than 1 hour or so. And if there are questions, maybe you can put them in the chat, and I'll try to have a look. I'll put it on the side, so I'll have a look, and I'll definitely find some time to answer your questions. So this first part, so that'll be a short introduction. Then I'll try to explain the principle of Bayesian analysis in very general strokes, and how they are applied to industrial hygiene measurements, and how Bayesian statistics permits to have another look at uncertainty. You remember yesterday I showed that, thanks to Bayesian statistics, we could have this picture of all the possible true distributions that are suggested by my own sample, with the 1,000 potential values for the 95th percentile, is 1,000 potential values for the exceedance fraction or for the arithmetic mean, and how we use them to calculate confidence intervals and confidence limits. today I'll show that this can be used for easier to communicate ways. So we'll see about that. So as an introduction, I'll try to give a one slide a glimpse of some key aspects of Bayesian statistics. So there we go. So we have a certain quantity of interest. For example, the proportion of exposures above the OEL. So I'm looking at the other side of the coin, not the 95th percentile as we used yesterday, but the exceedance fraction. So of course, we would like to make sure that this is below 5%, the consensus for an acceptable situation. So one key characteristic of Bayesian statistics is that you need to state what you know in advance about the parameter that is of interest to you. So you need to state you need to render explicit your state of knowledge about, in this case, the proportion of exposure above the OEL before any data collection. So of course you can say I don't know anything. So for the exceedance fraction, you would just say it is anywhere between 0 and 100%, and every value is has the same chance of being true. But you can also use various sources of information to say you know a little bit about the exceedance fraction. And in this very arbitrary example, maybe the hygienist has had a long experience of that kind of workplace and said, well, this workplace, this current workplace, seems to be on the cleaner side compared to my experience of workplaces of the same type. And so I would say, well, I don't know a lot about the exposure, the exceedance fraction, but I know that it's probably not above 50%. So I would say it's between 0 and 50. So you see, it's not a lot of information, but it's a little bit of information. And then, just as in traditional statistics, the Bayesian framework is going to interpret your data to retrieve information about your parameter of interest. And in this example, that would be the data that you have would suggest that the exceedance fraction is between 14% and 34%. So that's high, that's much more than is allowable. But so this is the information in your data. And the characteristic of Bayesian statistics is that it's going to combine your prior state of knowledge to what the data has to say. So the information that you defined a priori is merged with what the information coming from the data to obtain what we call the posterior knowledge about the situation. And you see that in the case where you said you knew nothing, the results only come from the data. So it's the same confidence interval. But in the case where you stated some prior knowledge, and because it was somehow coherent with what the data had to say, in the end, you see that the confidence interval is thinner compared to the one above. So it means that the merging of these two sources of information has reduced the uncertainty. Okay, so that's the essence of Bayesian statistics. And one thing that I want to note is that when you choose to make a Bayesian analysis with the option equivalent of saying, I know nothing about this parameter, you're gonna obtain results very similar to traditional statistics. And the second thing I wanted to state is that this possibility of merging information with your data is potentially very useful. And you might have heard that, with Bayesian statistics, you can deal with small sample size, you need less data. And it is indeed true, because because in a way, the prior information you add to your data counts as samples in a certain way. But you need also to be aware that it is a double-edged sword, because if your prior information is of poor quality, this poor quality is going to be translated to the final result, right? It's exactly the same as the data. If your data is of poor quality because you didn't take representative samples, it's also going to affect your results. So both types of information, the prior information that can come from your expertise, from a leak review, from historical data, you need to be confident in it, just as you need to be confident in the quality of your objective measurement data. So I hope this gives you a very, a glimpse about Bayesian statistics. So going a little deeper into the principles of Bayesian statistics, this is an excerpt from the Wikipedia page. And this very short paragraph is very clear, I think, if you want to have a look at that later on your own. But, some essential points that I wanted to underscore. So it's a theory in the field of statistics where probability expresses a degree of belief in an event. So we start with a belief about something, and the other key things I wanted to underscore is we use Bayes' theorem to update these beliefs after obtaining new data. So you see, to make a link with what I just said, we state a prior belief about a situation, and we update that belief with the measurements, for example, that we took in a certain situation. So on an anecdotal side, Bayesian statistics have appeared, have been invented, so to speak, in around the 18th century. They were developed mostly by Reverend Bayes and a French mathematician called Laplace. And they have been used increasingly over recent decades in the 20th and 21st century. And there's a very nice, it's like a novel book written by Sharon Birch, explaining the many adventures where Bayesian statistics were used successfully, among other, the secret communication machines used by the German army during World War II was cracked thanks to Bayesian statistics, and it was related in a movie not very old called The Imitation Game, where was the biography about the mathematician Alan Turing. So it's a very nice book if you're curious, and probably you can get it for very cheap now. So here's a general principle of how Bayesian statistics work. And if you want to go a little deeper, I put some references at the end of this of the slideshow that you have in your documents. There are some very well-made videos on YouTube about Bayesian statistics, very well explained. So as I said earlier, the essence of Bayesian statistics is that you need to define what you know about your parameter of interest in advance. So let's say we come back to the 95th percentile. We want to know about the 95th percentile. We need to express what we know about that that parameter in advance. And how do we do that in Bayesian statistics? Well, we saw yesterday that an uncertainty distribution is how Bayesian statistics tell us about what we know about a parameter. But yesterday we mentioned it as what we know about the parameter at the end of the analysis, generating these 1,000 values of a 95th percentile allowed us to draw a histogram and a density curve. And this histogram and curve reflected what we knew about these parameters. So the likeliest values where the density was high and less likely value on the side. So to express this prior knowledge, we do exactly the same thing. So we need to draw, so we can, and even we can do it manually, we draw the distribution of uncertainty about that parameter, reflecting our own knowledge. So just, and I put the same little explanation of how to interpret a density curve as yesterday. So we draw this uncertainty distribution with a shape where the highest, then the densest parts reflect values that we think are very likely, and parts where the density is low, like here and here, reflect values that we think are very unlikely. So here I drew like a symmetrical bell shape, but you could draw anything. And for example, if you think that any value between here, as I show with my pointer, and here on the right are equally plausible, well, then the uncertain distribution would be just a horizontal line, like we call that a uniform distribution. So all the values between here on the left and here on the right would be equally plausible. That would mean to say my prior information is that within that range, every value is equally plausible. That is already some information because we are defining a range. It's not from minus infinity up to plus infinity. It's just within one range. But within that range, we think all values are equally plausible. So my example here that you see on the slide is not a uniform distribution. We think that the values here near the center are more likely than the ones on the side. And so this is really, we as experts, using various means, either personal experience or lit review, mechanistic models, we define this prior information. And now the information coming from the data is going to be extracted using the statistical model, the log normal, the knowledge that we use the log normal model. And so this is where the mathematicians become useful, so to speak. And this data extraction is called the calculation of the likelihood function. And the likelihood function, its essence, I try to phrase it as clear as I could. So given a statistical model, so here the log normal distribution for measurements, the likelihood is going to measure the likelihood of observing our data across the universe of parameter values selected in the prior. So if I try to state that another way, what the machine, the engine, the equations are going to do is they're going to scan the range of value that you define here could exist. So let's say here between this value on the left and this on the right. So the likelihood is going to look at the first value here and measure how likely is it that the 95th percentile is equal to that value given my data. And then it's going to go to the next value in a sequence, and it's going to scan the entire range of possible values. And for each of them, it's going to measure how likely was it that the observation would come from a distribution where the 95th percentile is equal to that particular value. All right, so you can see that we're going to have similar information in the shape for the prior. We have something that scans the range of potential value and gives them a likelihood, but according to my own prior opinion. And you're going to have something quite similar, also scanning the ensemble of values, but this time the likelihood is not decided by myself, it's calculated using the data. And you can see that at the end, we are going to get a result that is, again, an uncertainty distribution, but is going to combine the two types of uncertainty, the prior knowledge that I decided myself and the knowledge that comes from the data, and both being combined into what we call the posterior distribution, uncertainty distribution. So I'm going to use a simple example to get even a little deeper into that explanation. And because it's a very simple Bayesian model that doesn't require intensive computation and can even be done by hand, I'm going to use the example of estimating the mean of a normal distribution. And even simpler than that, a normal distribution for which we know the variance. So there's only one unknown parameter in that problem. It's we don't know the mean. And the population of interest is the mean of the height of male industrial hygienists. So I chose industrial hygienists because this is my population, and men, because in order to not mix men and women, because then if you mix men and women, the distribution of their height is going to be is going to have two summits, because men and women don't have the same height distribution. So this is our problem. We want to estimate the average, the mean of the height of industrial hygienists. And so the first thing I need to do is to select the prior. And this is my own expertise. I cannot ask the statistician to help me for that. This needs to come from expert knowledge about the subject matter. So I need to state what I think in advance about the average height of male industrial hygienists. So what I did, because I'm not a height specialist, I thought, well, maybe hygienists, we are a special bunch of people, but probably in terms of height, we are not so different from the general population. So I decided that as a starting point, I would use the average height of all people in Canada, all male people in Canada. And so the average height of male people in Canada is 175 centimeters, so 1.75 meters. And so I hope you are okay with me using the international units of centimeter and not inches and feet, because I'm lost in these North American units. So the most likely value for me is 175, but I need to draw some uncertainty around that value, because if I don't allow uncertainty, the data is not going to be used for anything. So I say, okay, the likeliest mean would be around 175 centimeters, and it might be, and then the likelihood decreases, and it might be as low as 165, but it's not super likely, and it might be as high. The true value might be as high, as 190. But you see that below 160 and above 190, my personal opinion is that it's almost impossible that the mean of male industrial hygienists would be outside this range. So this would be my prior definition. So to really underscore that this is my choice, I could have selected another type of information. So in this case, I could have said, well, any value between 150 centimeters and 200 centimeters makes sense. So, and I have no reason to believe that any one of these values is more likely than the others. for the average height of industrial hygienists. So that could have been a choice. And another potential choice would have been this one, where I still use a value that is more likely than the others. Again, the national average in Canada. But then I would use like this more linear decrease in likelihood, going to the two smallest possible and highest possible values that I chose, right? So you see, it's really my personal idea about the parameter is unknown. So for the calculations that I will show, the model used the first one I showed, the bell-shaped prior. So now we are having a look at the data itself. So I interrogated 5 colleagues, male colleagues, and in Canada, and they provided me with their own height. So my data is actually a sample of size 5 measurements. And so you can see right away that my male hygienist colleagues, they seem to be fairly tall people. But that's my sample. I try to be representative so that it would be representative of male hygienists in Canada at least. And just for the I want to mention that this is a fake data set, so don't think that Canadian hygienists are as tall as that. So just for the illustration, so this would be my data. And then I'm going to show how what we obtain for the likelihood. When the model, the calculation itself scans all the values between 150 and 200 centimeters and calculates how likely it would be that we would observe this value if the true value of the mean height was 150, 151, and so on and so forth. And this is what we obtain. So you see it's the familiar shape like of an uncertainty distribution, a density curve. And you can see that as quite intuitive, I think, the very low value in my range of plausible values have a very or null almost likelihood. So of course, it would be very unlikely to observe the heights we have observed, which are all around 190 centimeters, if the actual mean height of hygienist was 150, I would be very unlikely to observe what we observe. So the likelihood here is very low. And you see that as we approach the range of values that look like my observations, the likelihood increases, and then it is maximum for a hypothetical mean of 190 centimeters. And then it goes back down. So this is what my observed data suggests. And finally, to get at the results, so this is the combination of all sources of information. So you see in red was my prior information, centered at 175 with plausible values as low as 160 and as high as 190. You can see in black what was suggested by the data itself. So more centered about 190, but also plausible between, I would say, 180 and 200. And then you can see in green the results of combining the two. And so you see two things. That first is you clearly see that the center of the green distribution really looks like a weighted combination of the two other centers. So you can see the combined influence of the two distributions. And the second thing is that you can see the green, the posterior distribution is thinner than the two others. And of course, a thinner uncertainty distribution means less uncertainty. And if we draw confidence intervals using that green distribution, they're going to be quite thin compared to the ones we could draw for the prior or the likelihood. So this is a simple model, but it renders very visible the way that the combination of the prior and the likelihood is actually done. So one thing to note is that except for very simple examples, like the one I just described, we never get an actual equation for the posterior distribution. Like here, you see this is a density curve, so it's written thanks to an equation. But we, unfortunately, for most practical Bayesian problems, there's no analytical solution, so there's no equation for the prior. So what we do is exactly what I explained yesterday, is that we are able, without equation, we are still able to draw random values from the uncertainty distribution. So we are able to generate plausible values for the parameter of interest. So we don't get a curve, an equation, but we give a histogram. And yesterday I gave the example of 1,000 values. It depends, of course, of the model, but usually it's a bit more than that. For example, in ExpoStats, in the tool that we made at University of Montreal, the histogram we use is based on 25,000 values instead of 1,000. So, and we call that the posterior sample. So as a summary, so how do we interpret this graph? So we have the universe of hypotheses for the mean of industrial hygienists. And so, this gives us what we know now about this parameter. So the likeliest values that would correspond to a point estimate would be around 195. And but if we drew a confidence interval, it would be probably between 187 and 194 or something. So we would say that we estimate the mean of male industrial hygienists to be around 195 centimeters, but the true value is very likely to be between 186 and 194 approximately. So, as we did yesterday. And this is this represents our state of knowledge after we combine our prior information and the observation, of course, through the hypothesis of, whatever statistical model we use. And one last thing on the principle. So you see, this combination, and there's a tendency for us to see, okay, we combine prior information that's very arbitrary with objective data. And so if we have a bad prior information, it's gonna dirty, in a way, posterior information. So we should be very careful with the prior information and maybe very suspicious of it. And maybe we should even always say we don't know, so that only objective data is used. But, I think we need to recall that this objective data that we measure, it's not perfect either, because when we go and measure some days or some moments, usually we are not selecting them randomly in the statistical definition of random. So they might be not perfectly representative. We might not have a perfect measurement methods or devices. We might also not forget to monitor some important moments in the day. So in my own view, of course, it's my own personal opinion, but both types of data, they are imperfect. And I see this combination as a combining imperfect sources of information to obtain the best possible portrait of the exposure situation. And in a way, both situations counterbalance each other. So, even for example, if my sample of hygienists, by mistake, I only interrogated tall hygienists, well, then this mistake would be countered in a way by my prior that was based on the whole Canadian population. So you see these two, by combining the two sources of information in a way, you kind of mitigate each method's own limitations. So I have maybe a little bit more balanced vision about which of the two sorts of information provides the best information. All right, so now let's finish this part about the Bayesian introduction, first applying it to industrial hygiene and then seeing how it helps us dealing with uncertainty. So going back to your field of daily work. So which Bayesian model do we use for Bayesian, when we use Bayesian statistics in industrial hygiene? Mostly now, and it might be developed in other areas. So where the statistical is the log normal distribution, and I think I mentioned yesterday, the parameters of interest to us for risk assessment might be the exceedance fraction, the 95th percentile, the exceedance fraction, the arithmetic mean, but we get to them using the geometric mean and the geometric standard deviation. So the parameters that we are going to estimate with our industrial hygiene Bayesian model are geometric mean and geometric standard deviation. So we need to define what we know in advance about these parameters. Then we get histograms, 25,000 values for each of them. And then we use these to get to 25,000 values of the risk parameter of interest to us. So I'm going to go through that with you. So this is an example using our own tool at University of Montreal, ExpoStats. And it's interpreting a sample from the lead dataset that I mentioned yesterday. So we have, you see at the bottom here, we have 6 samples, 6 measurements that are going to be used for the likelihood. And so for the priors, this is the priors we use in ExpoStats. So at this moment, you cannot change the prior in ExpoStat. It's like it's a generic prior for everyone, everything. And we think it's applicable to most calculation problems, but we probably will change that, if not this year, then the next. So for the geometric mean, we have a very uninformative prior. So it says very little about what the geometric mean. You see that in the log scale, it's a uniform distribution between the exposure limit divided by 10 to the 9 and the exposure limit divided by multiplied by 10 to the 9. So, to most practical extent, it's almost between 0 and plus infinity. So we say almost nothing about where the geometric mean is, or might be. Now for the geometric standard deviation, you can see there's definitely some information here. And you see that our prior says that typical GSDs would be around 2. And they could be also quite high, up to 6, but above 6, it becomes fairly unlikely according to us. Right? And where does that distribution comes from? Well, it comes from the studies I mentioned yesterday. There's 5 or 6 studies published over the last decades that reported summaries of a large number of geometric standard deviations for many types of work situation, many industries, many different risk factors. And if we make a histogram with these values, we get this shape. So for us, this shape represents the state of knowledge of GSDs in the general industry. And so what it means in terms of the calculation is it means that if your data set suggests very high GSD, like 8 or 10, they will tend to be pulled back towards lower values by our prior, except if you have a large number of points. So for our system to allow you to have a high GSD, you will need to be very convincing with a lot of data. Otherwise, our system will pull the estimates back towards more typical values. So of course, this influence is most marked where the number of points is very small, like between, below 3. As soon as you reach 5, 6, the data will come with its own information about variability. So you see now, let's look at the update process. So you see here, you started with almost no knowledge between almost 0 and plus infinity. And after updating, creating the likelihood and merging the likelihood with the geometric mean prior, you see our histogram of 25,000 plausible values for the geometric mean. So you see now it's much thinner. It has a kind of a almost symmetrical shape, not exactly. And you can see that most value would be between 10 and 30 micrograms per cubic meters, with the most likely value around 18. So you can see a lot of updating, almost no knowledge. And now we know that the most likely value would be between, let's say, 12 and 30, right? So you can visualize the update process. Like the arrow is like an idea of a confidence interval. If we look at the GSD, you can see also that there was an update. And so initially, we started with plausible values between, let's say, 1.1 and 6.7. And thanks to the data, this is much thinner now. It's between, I would say, 1.5 and 3 at the most. So there's still quite a lot of uncertainty around this variability estimate. It's, estimating variability is very difficult. So that's why the thinning is not as pronounced as for the geometric mean. But still, you can see there was a decrease in the uncertainty around this parameter. So we have now our 25,000 values of geometric mean. We have 25,000 values of geometric standard deviation. And this gives us, there's a simple equation relating 95th percentile to geometric mean and geometric standard deviation. So it's very easy. And in some longer courses, I actually have people do it. So I give them an Excel file with the 25,000 values. So you can actually easily calculate 25,000 values for 95th percentile. And this is the posterior sample for this parameter. This is the state of knowledge about the 95th percentile after the Bayesian analysis. And so how do we interpret that? So I'm going to start with the traditional way, which we had a look at yesterday. So what you can see here is twice I drew the sequential plot of the, well, I didn't draw 25,000 values for, clutter reason, but I used only 1,000. So you can see here, I drew my 1,000 values of potential 95th percentile values in the population. So it's plausible true value, let's say. And what I remark is that 95% of them or 950 are greater than, are smaller than 100. So what it means, if you remember yesterday, it means that 100 milligrams per micrograms per cubic meter represent a 95% upper confidence limit for the 95th percentile. So I'm sorry for the sentence with 95, 95, but that's actually it. So you see, I have my posterior sample and I find a value that is greater than 95% of the rest. And this is represent this upper confidence limit here. So I am 95% sure that the true 95th percentile is below 100 milligrams per cubic meter. If I can do that with 950, I can also do the same with 700. So I find the values in my sample of 1,000, which is greater than 70% of the rest. And this value is 50. And so this value represents a 70% upper confidence limit for the true value of the 95th percentile. And you see the point estimate here, I would obtain just by finding the median of these 1,000 values. And so you see, I can get to the result, the traditional results. I can say the point estimate for the 95th percentile is 42 micrograms per cubic meters. A 70% upper confidence limit is 51, and a 95% upper confidence limit is 100. But I'm sorry, there's a small mistake in the unit here. It's microgram. And so you see, we can use the posterior sample of 1,000 values in this case to obtain the traditional point estimates and confidence limit. But I said we could go to more interesting results and easier to communicate, and this is how we do it. So the other way to interpret these 1,000 values is to draw the OEL here on that plot and to count how many of the plausible 95th percentile values are below the OEL. So all these plausible values, which I put in green here, they represent values of the truth that correspond to an acceptable situation, right? And all the ones I put in red, which are above the OEL, they represent plausible values that correspond to a non-acceptable situation where the 95th percentile is above the OEL. And thanks to the Bayesian model, and if even I could use Excel once I have my 1,000 point, I can determine that 320 or 32% of the values are above the OEL. So to say that 32% of the plausible values for my parameter are above the OEL, you can directly state that in the following way. You can say there's a 32% chance that the situation is unacceptable. That's exactly how you translate this calculation here into a statistical conclusion. 32% of the plausible values are above the OEL. This means that basically the chances that I have an overexposure problem are 32%. So no point estimate, no upper confidence limit, no 70, no 95. You just take directly the probability that you have a problem. And I hope that you agree with me that this renders the communication of risk much easier. You can say to a boss or a worker, our analysis suggests that there's one chance is 3 that your situation is problematic. So, and this is the way that we framed our tools at University of Montreal. So we define overexposure, and it's fairly flexible, but a standard way would be saying the 95th percentile is above the OEL. And our tool calculates the probability that this is true. So the chances of a problem, to speak simply. And we call that overexposure risk. So the risk that overexposure is indeed true. So now, we discussed yesterday. But now we need to transform this number into a decision. So do we act? Is 32 too high? What is too high? What is low enough? What is acceptable? What is not? So we can apply exactly the same framework as we discussed yesterday. So that's why you see the three colors that we have here, and this is one of the outputs of ExpoStats. And so if I go back to the scheme that I showed yesterday, that's proposed in the series of videos from the American Industrial Hygiene Association. So we can use exactly the same framework, but use the probability of a problem instead of upper confidence limits. So for example, the acceptable zone, which yesterday we said we need to be 95% sure that the 95th percentile is below the OEL. The equivalent using risk of overexposure is we want the risk of a problem to be smaller than 5. And it's exactly the same, but it's expressing the same thing using the notion of chances of a problem. So if the risk of overexposure is below 5%, very unlikely that there's a problem in that situation. We say it's green. If the risk of overexposure is between 5 and 30, we say it's tolerable. And if the risk of overexposure, so the chances that there is a problem, are over 30%, this is problematic. This is something where we need to act, right? And you can see the correspondence between the traditional interpretation scheme we saw yesterday and this new one. So I believe that this left side here is easier to communicate, but you are the ultimate judge. And there's only a few slides left before we can take a break, and then I'll make a little summary about current recommendations. So I guess that some of you may be familiar with the AIHA exposure control categories. Where instead of saying this is unacceptable and then this is acceptable, we say, this is acceptable, but this is, instead of red versus green is red, dark orange, light orange, yellow, green, blue, and then so we see that we'll be able to get a lot of information about these categories. So the way it works is that you see here, we split the uncertainty distribution in two parts, the parts where the 95th percentile is above the OEL and the part where it's below. So just a two-part separation. Nothing prevents us from splitting the uncertainty distribution in more parts. So this is what I did here. So here's the OEL. So I still have my 320 points above the OEL. But I can also create an area where the true 95, the plausible values are between the OEL and half the OEL. And also I can have an area, I can put the OL divided by 10 and the OEL divided by 100. And I can count for each of them how many of my plausible values are. So you see here, I still have 32% chances here that the situation is problematic. I have 62% chance that the situation, the true value would be between the OEL and the OEL divided by 2. And I have a 2%, so you can see there's a small number of yellow points here that were between the OEL divided by 2 and the OEL divided by 10. And then there was nothing lower. And this I can transform into what was named the BDA chart. So sorry, Samantha, I don't know, this is an old question, but I just saw your question. I'll answer before the break. So you might have seen this scheme of, these risk ratings from the AIHA. They also call them exposure control categories. And since we now have access to the entire uncertainty distribution, we can split it into exactly these categories and to create what you might have heard called the BDA chart. So a BDA chart, the BDA, someone named that Bayesian data analysis. There's a tool called like that from a colleague called named Paul Hewitt. So the BDA chart tells you, well, the chances that your actual exposure control category is a category 4 is 32%. The chances that it's a category 3 is 66%. And there's a slight chance that it will also be a category 2, and there's some unlikely that it would be any of the other categories. So you can see, thanks to the ability to split the uncertainty distribution, we can get access still to the risk of a problem. It's still the category in red. But you can also say, well, the likeliest category in this case would be a category 3 for management purposes. So you see, I have presented these 3 ways of managing risk. So there's the traditional one, where we use confidence limits and confidence intervals. And that's been existing for a long time. And the 2 newer schemes, which are, I would say, more probabilistic when we express uncertainty as the probability that. So this is the expostats where we have the probability of overexposure, and where we have, this consensus scheme where we say, it's good when the risk is below 5%. It's tolerable when it's between 5 and 30, and it's unacceptable when it's above 30. And then you have the BDA graphs that allow you to, select the most likely risk category if your company or you use the AIHA bands. But even in this graph, you still get the risk of overexposure, which is here is 16%. Okay, so so these newer ways, I think, they improve risk communication, but for practitioners, we need to be able to switch between them, with ease, because it can be a bit confusing, I guess. I've been teaching about that for a long time, so I switch between all these approaches fairly easily, but it's something that you need to acquire. So before we go to the break, we can do the question. There's just a question before I finish. We can do a small 5-minute break, during which I'll answer Samantha's question, and then I'll continue, let's say, starting at, we can take 10 minutes, so I can answer Samantha's question, and she can also take a break. All right. So an action limit, or so your sentence is complicated too, Samantha. An action limit of 2.5% is equivalent of traditional method at 95% UCL. So your action limit of 2.5%, this 2.5% would be an expression of a confidence or a percent or an exceedance fraction. I'm not sure I understand, Samantha, if you can clarify.
Yeah, you referred to a few slides back.
Yeah, I'm gonna
5%.
share again so I can.
I think you sort of answered it in the subsequent slides.
I lost my. Okay, right. So that would be. It was yesterday or today?
No. Just go forward again. We just looked at something.
This one?
No. This. Oh.
This one maybe.
It was when I think you referred to 5%. We were looking for 5% as an acceptable limit using the posterior method. Maybe the one with maybe this one. This one, yeah.
Yeah.
Is it one of these? Yeah, the 5% on the top.
Yeah, that's a good point. Maybe there's something I meant to say, but I didn't want to delay the break. So is that this 5%, we need to be, there's a, because we have two 5%, right? And we need to be very careful about that. There's the 5% first that helps us define the notion itself of overexposure. We say overexposure is the 95th percentile is above the OEL. But this is equivalent to more than 5% of exposure levels above the OEL.
Yes. So we would say.
So already just defining overexposure, there's a 5% lurking somewhere. So let's say now we know that, and let's say now we talk about overexposure, and then this green category here is the probability that overexposure exists, right? So this 5% here is a chance that something happens. So it's the chance if I use the two 5% in the same sentence, we say here this is acceptable if the chances that more than 5% of exposure levels are above the OEL is less than 5%, right?
Yeah. So we use the term action limit, which is.
So your action limit is it for the chance of a problem, or is it for the proportion of exposure levels?
It's probably a bit cruder than that. It's simply if our 95th upper competence limit is equivalent to the OEL, obviously that's that's the point where you're going over, you've hit that exposure point. Anything above that is overexposed. But from an action perspective, we sort of have an alarm bell clicking at 50% of the OEL. So it's, but I think your subsequent slides have, I think my simplistic interpretation at this point of the presentation is exactly that, too simplistic, because here you've got your OEL divided by 2, which is what I was thinking of in my head. That's what I wanted to know, is where is that?
Oh, okay. So
conservative action limit, yes.
So basically, you look at the sum of the range of you look at the chances that your true 95th percentile is above the OEL divided by 2.
Yeah, and it's only a theoretical safety net, I guess, a bit similar to the banding IHA AIHA method, which is not something we use. So we would just say,
Okay.
you're at the OEL, that's now you're in a problem area, or you're at the you're 50%, you're up, sorry, your 95th upper confidence limit is at 50%. We're not panicking, but we're saying now we need to start looking
Oh,
for.
I understand. I think so. If
So
I
it's a
go
practical
here,
thing. Yep.
so basically you use that value here, an upper confidence limit on the 95th percentile, but you compare it not with the OEL, but with the OEL divided by 2 as a
Yes.
action
Yes.
trigger. Okay.
Yeah. Perfect. Yeah.
Yeah. No. Yeah. Okay. I understand. So yeah, of course, it's also it's a way to to act early, so to speak. Yeah.
No, I appreciate that. I was probably popping it in there while it was fresh in my mind, but yeah, we sort of got to it anyway. Thank you.
No problem. Thank you for explaining.
Yeah, I'll let you have a quick break as well.
Fill my cup of coffee.
Okay, ladies and gentlemen, we will have 5 to 10 minute breaks from now, and please be back by in Jakarta time 8:25. Yeah, thank you. So Jerome, we are having now for about 10 minutes. Is that correct?
Yeah. So well, this is the there's only 4 minutes left. 4 minutes left to the break. So if some people are back already, I won't start, but if some people are there, I'll copy paste back in the chat the polling website because I have a small question when we are back from the break. And yeah, I just realized something. Samantha, are you still online? She's a break. In the chat. Okay, so I think we shall start back. So here is my question. Okay, so you should see this question on your screen, and if you have gone to my small polling web page, you should be able to select what would be your opinion about this question. So it's a question, of switching between various approaches. And what we tell you here, we provide you with what we call the BDA chart, with the probability of each category. And we tell you that there's 22 or so % chance that the true 95th percentile is above the OEL, 28 that it's between the OEL and the OEL divided by 2, and 48% chance that it is below half the OEL. And from that, it's a difficult question. We ask whether the 70% upper confidence limit on the 95th percentile, is it greater than the OEL, smaller than the OEL, or you think that there's not enough information provided here to allow you to decide. So it's switching from the from the BDA graph approach to the traditional interpretation. From that graph, what could we say about a 70% upper confidence limit? Leave another minute. All right, so I have my 10 answers. Let's have a look. 12 now. Okay, so well done. The majority has the right answer. So indeed, this graph suggests that the 70% upper confidence limit would be smaller than the OEL. And why is that? Well, the key information here is that the probability that the 95th percentile, we are told, is 22%. And so the probability that the 25th percentile being above the OEL, sorry, I didn't finish my sentence. So the probability that the true 95th percentile is above the OEL is 22%. Okay, so 95th percentile above the OEL, this is what we call overexposure. So this tells us that the risk of overexposure or the risk of a problem is a 22% chance. And if I go back to my scheme summary here. If the risk of overexposure is 22%, it means we are in this region here tolerable, you know, risk of overexposure between 5 and 30. And so it means that while the UCL, the 95% upper limit would be above the UL, but the 70% would be below. Another way to look at it is to go through the motions of transferring from risk of overexposure to upper confidence limit without looking at this scheme. So if I say the chances of overexposure are 22%, right, it means that the chances of overexposure are below 30%, smaller than 30%, right? So the chance of overexposure is below 30%. So it means if I reverse that, it means the chance that the chances that there is no problem are above 70%, right? And so it means if I go to that using the upper confidence limit, is that I am at least 70% confident that the true 95th percentile is below the OEL. And this is the definition of a 70% upper confidence limit below the OEL. So I'll let you go through that very progressively. And there's a correction at the end of the documentation. It's something it's helpful to switch between these various approaches to clarify our head and not, you know, confuse the, the overexposure criteria and the expression of uncertainty. All right, so to wrap up with the Bayesian side of this presentation. So in my opinion, are features of very interesting in industrial hygiene of Bayesian statistics. So I mentioned it, the possibility of informed priors, which might help reduce costs associated with sampling. And I added here some potential sources of information for priors. So for example, at University of Montreal, we have a prototype model where there's a data set of silica measurement in the construction industry created from the literature that creates a prior exposure assessment for a specific tasks. And then people can add their own measurements to get a posterior, that's the agglomeration of their own measurements and the historical prior exposure assessment. So it's one of the first prototypes where you have this historical database that serves as a prior for an exposure assessment. And my opinion is also that facilitating risk communication is a big plus of Bayesian statistics. You can express risk as the chances that we have a problem. And there's also two things that are very interesting. The first is that the Bayesian statistics, they allow optimal treatment of non-detects. So you don't need to replace them with the yellow Q divided by 2. You can just enter smaller than something or even between something and something else in tools such as Expostats. And there's a couple of publications demonstrating the advantage of doing that. And also, it will be possible very soon to tell your exposure assessment tool that each measurement comes with a sampling and analysis error of 12%, for example. So I said yesterday that we usually this error is negligible, and it is. But thanks to Bayesian models, we don't even have to make this assumption. We can say this measurement has a 12% error of measurement, this one has a 15%, and then the calculation is made without assuming anything. So that's going to soon be present in our tools, probably in a couple of years maximum. And to a last slide. So, because people are interested in to know how Bayesian statistics compare to frequentist statistics. If you use, for example, IHStat versus ExpoStats. So both would use the same distributional assumption. So we hope that the log normal model is reasonable. You need a random sample in both cases. They can both be used to derive confidence intervals. In Bayesian vocabulary, confidence intervals are called credible intervals because Bayesian statisticians are more modest. And both types of analysis will lead to similar results when the prior distribution is non-informative. So when we say we know very little, we will get similar results as between the two methods. But I think Bayesian statistics, they permit prior information. They handle censored data way better. And since we often have censored data, that's a big reason to switch. And they allow, in my opinion, better better uncertainty communication. But you need a tool. You cannot use an equation in a book to calculate Bayesian confidence intervals and, for example, the risk of overexposure. So the wrap-up bottom line, Bayesian statistics are becoming widespread in many areas of science, and they are already, I think, widespread in industrial hygiene. They offer a lot of flexibility, and the tools and practitioner level manuals are appearing, are very easy to find now. It was not the case 10 years ago. And users concerned with the use of informed prior can simply use uninformed priors. And also, it's not a magical wand. We still need to be very careful in how we create our priors and how we collect the data we want to interpret. So the other slides are for your reference, a bunch of manuals and websites where you can find some useful tutorials about Bayesian statistics. And for this last 25-minute part, an overview of a number of current strategy recommendations. So this is not a representative sample. It's based on my North American bias. So they are in English and were published in Europe and North America. There might be others. So I'll give some information about the NIOSH strategy, which has been published a long time ago, the AIHS strategy, the British strategy that has a very specific part, and the recent European Community Guideline, EN 689. So again, this is a general scheme of risk assessment, and really, some of these guidelines are very detailed recommendations about all aspects of this process. And in, myself, I will focus entirely on the, statistical interpretation of collected measurements, which is the focus of this course. But, these guidelines are much broader, of much broader scope than that. So the NIOSH strategy was published in 1977. And already then, they were proposing that, the employer should attempt to limit the probability of employee overexposure to 5%. That is, no more than 5% of an employee's true daily exposure averages should exceed the standard. So this proposal that the number of days in a year above the UEL should be less than 5% was already proposed 50 years ago, more than 50 years ago. And even the statistics were very detailed in the, all the equations to calculate the 95th percentile and upper confidence limit, and even the exceedance fraction and were present. There was a very well documented monograph. But somehow, and maybe to facilitate the work of OSHA inspectors, so regulatory inspectors in the US, this the main strategy that came out of this, the practice that came out of this monograph was to compare one measurement from the worst case employee to half the OEL. And if it was smaller than that, it was okay. If it was not, you need to continue sampling until one measurement or two were below that action limit. And with the added difficulty that it's not always easy to find the worst case employee. And there was a lot of criticism of that strategy, with a lot of demonstrations that having one measurement below the half DOEL does not guarantee at all that less than 5% of the exposure levels are above the OEL, as was the objective. There was many papers about that. And there was a table here that has like a number of samples required, depending on the size of your exposure group. So several organizations mistook that table for like a generic recommended sample size table, whereas it had the very specific objective. It was guarantee that you find a worst case employee. So if you don't know what the worst case employee is, and you have a group of, you need to take 9 measurements, and then it's very probable that the highest of your values correspond to the actual worst case employee. So not a really super useful table, but it was, some organization that treated it as ideal sample size for risk assessment, which is not the case. And in 2007, there was a workshop, and there was some communication internationally that this recommendation from NIOSH was being updated, and then it became, and then there was silence, let's say. And then in 2022, I saw a publication that a quite famous researcher in our field, Gurumurthy Ramachandran, was leading a team to update the guideline, and that it would be done within the year. So I was very interested, and so it took a little more than that, but finally, this year, if you have the chance of going to the AIHA Connect conference, which is in May in Columbus, Ohio, there is a 1-hour session where they will describe the proposed update to the NIOSH exposure assessment strategy. So after 50, I can't even calculate now, more than 50 years, we are going to get an updated NIOSH guideline for exposure assessment and risk assessment from airborne chemicals. So very exciting. A brief overview of the AIHA strategy. So, you know, they have their big monograph about risk assessment, and a centerpiece of the risk assessment for the AIHA framework is to classify your exposure groups into these exposure risk management and control categories. Well, you see the category 4 is when the 95th percentile is above the OEL. This is where you need to implement controls. And below that, you know, these are situations where, yes, the 95th percentile is below the OEL, but like there's a progressive decrease in the severity of the recommended management actions when we get to lower exposure levels. So in category 3, it's acceptable but close to the problematic area. So we need to watch these situations somewhat closely. So, you know, for example, here there's required exposure monitoring and inspections and so on and so forth. And then as you get further away from the OEL, the recommended actions are less. So, for example, you would start your risk assessment by maybe choosing the category based on models or expert, and then the groups for which you are in category yellow to red, we maybe support your classification with actual monitoring and so on and so forth. And the main steps, you know, is that you should monitor exposure where you think that there are possible exposures above at 1/10 of the OEL. And then you need to take 6 to 10 samples per group, which, of course, if I made a poll, I guess at best, most companies would have selected 6 and not 10, unfortunately. And then you estimate the 95th percentile and the confidence interval. And you use this information to select your risk category. And I wanted to, because it's shown in the AIHA monograph, you know, from where comes the 6 to 10 sample recommendation. So it's a kind of cost-benefit analysis. And it's not even based on the log normal model, it's based on the normal distribution. So basically, the group of people that initially created this recommendation, they looked at the width of a confidence interval around the mean of a normal distribution as a function of the number of samples. So you see, of course, you start with 2 samples. Your confidence interval around the mean is very wide, and you see it thinning as progressively the number of samples increases. And basically what you can see that there's a point after which, like the point of diminishing returns, so to speak. So there's a point after which you pay for an additional sample, but the added thinning of the confidence interval becomes very small. And of course, it's very visual. And if I asked you, where does it fail to be enough thinning per added measurement, probably that would be a wide differences across yourself. But the authors of the monograph, the AIHA monograph, sorry, they decided between 6 to 10 measurements, there was not a lot of added value when you increased your sample set. And they did the same for the estimation of variance. because, you know, the risk parameters we use, the 95th percentile, the exceedance fraction, they depend on both the mean and the variability. You see, it's more difficult to judge, as, you know, there's no really real flattening anywhere here. And, you know, but they decided it was, you know, maybe here between 8 to 12, you know, more difficult to judge here. But their overall recommendation was that at least 6 to 10. So that's where it comes from, the 6 to 10 recommendation. So to answer your question, Aristides, I don't know that the publication itself would be released, but at least there would be a presentation of its content at the conference. But I don't know when, you know, an official NIOSH document would be released. I don't know when it would be. So on to the British-Dutch recommendation. So it was published in 2011, and I was very lucky to have participated a little bit to it, but a tiny little bit, and I happened to appear on a paper describing its content, but really just because Trevor Ogden, then the head of the British Occupational Hygiene Society, needed some statistics to be calculated, and so he asked my help, but I really did very little apart from that, so I really don't deserve the presence in that paper. But that recommendation, I think, is very interesting because it addresses a very important question, the notion of the homogeneity of our exposure groups. So a bit of context, historical context. You know, the notion of a similar or homogeneous exposure group appeared at the end of the 80s in the scientific literature. The name was exposure zone when it first appeared in the papers. And then in their first monograph, AIHA coined the term homogeneous exposure group. And now you probably know that in current monographs, and we talk about similar exposure groups. And this name has been there since the 1998 version of the AIHA monograph, which is the version that I first met when I started in this field. And so what happened between the homogeneous and the similar versions is a number of studies by these authors who are quite renowned researchers in our field, that they collected information where they were able to actually quantify the amount of variation within exposure groups. So they collected, you see here some statistics, 45 studies, 83 data sets, representing around 15,000 measurements, and across approximately 200 exposure groups, representing 2,000 workers. So across many industries, many risk factors. And basically, so, you know, there's been a lot of debate about these studies, about, you know, what criteria did they use to declare something was homogeneous or not. But, you know, some essential results is basically they showed that our homogeneous exposure groups were not that homogeneous. And, you know, despite the debates and the discussions in letters to the editor, the main takeaway from these studies was that, you know, we should not take our homogeneous exposure groups for granted, but should be ever watchful of, you know, verifying whether they are indeed homogeneous. And one of the consequences is that the AIHA group became more modest naming, and so the groups are now similar exposure instead of homogeneous exposure. So the way that this strategy works is that basically it's like, for those of you familiar with the statistics, it's basically an analysis of variance model, where you want to differentiate between that situation here, where you see that each of these 4 workers have a similar exposure distribution, so their risk is similar, from that situation here, where you see that within that group, each worker has a fairly different exposure regimen, and some workers are clearly at risk, while some others are not. So the aim of this strategy is to differentiate between these 2 situations. So the ANOVA models is going to basically split the variance into a between worker component and a within worker component. So what you obtain is basically each worker ends up with his own exposure distribution. So you see here 4 distribution. So each worker has its own geometric mean, but you see that there's no index here, but because the exposure variability for each worker's exposure distribution is the same. It's constant. So it assumes that all worker distributions have the same variability called within worker variability. And if you take all the geometric means from the workers and create a histogram with them, you get this distribution where you have the geometric mean of the group, and of course, all values are geometric means from individual workers. And so the difference, the fluctuations across workers is called the between worker variability. So you see the total GSD is split between these 2 components. And of course, the between worker variability is going to tell us whether the group is homogeneous or not. And the way to calculate risk is to calculate the probability of individual overexposure. That is, how many workers could be overexposed, with overexposed having the same definition as we discussed. So basically, the ANOVA model allows us to create like a distribution of the worker-specific 95th percentile. So each value is a 95th percentile. And you can calculate how many of these are above the OEL. And so this would tell us how many workers, so to speak, might be overexposed. And of course, we want that to be limited. So this is the first recommendation that tackles this issue. So it's a 3-aspect, a 3-step proposal. So there's a screening step, and this is something we're going to see again in the European guideline, very useful, I think. So you start with a limited number of samples, because we all know samples are expensive. And if all samples are smaller than 1/10 the OEL, you can stop and declare the situation as acceptable. If any of these is above the OEL, you can declare the situation problematic. And this has a statistical foundation. If you cannot make a decision there, you calculate group compliance. And this group compliance, you see 9 samples minimum with some repeats on some of the workers. And here, the compliance is what we discussed, is basically if the risk of overexposure is above 30%, it's non-compliance. And then we need to test whether some workers might be at risk. And there, the group made an arbitrary cutoff. So if the risk of a particular worker to be exposed, or another way to phrase it, the proportion of workers that would be overexposed is above 20%, then that would be non-compliance. So it might be that the group is compliant, but that the workers, some workers might be ill protected. So that's it's a quite interesting recommendation. Not so easy to compute, and our tools that you have can help with that, but quite interesting. So since I'm arriving to the end of the time, I'll switch to the European guidelines that was recently, well, recently, it's been a couple of years now, updated in late 2018. And I like this recommendation quite because it emphasizes a lot the notion that there's a lot of variability in workplace exposures, and that we need to extrapolate a small number of measurements to this large number of situations, which are the target of our assessment. There's a lot of focus on trying to check the validity of the similar exposure groups. So, being careful about how we define them is fairly important. So Aristides, there's a recommendation that if your GSD, your global GSD in your data is above 3, you should try to make some verifications. So it would be like an alarm, so to speak. There is also a screening test. So if a small number of measurements are very, very low, you can stop. Or if any one is above, you can stop. So the aim is to limit the sampling effort in clearly acceptable or clearly unacceptable situations. And finally, if you end up going the full procedure, again, the number of samples is not mandatory here, but it's it start. I think the calculations in some tables in the appendix start at 6, but I guess 6 to 12 is the recommendation. And again, we find the same concept that we have seen. So overexposure is defined as more than 5% of exposure levels above the EOEL, just like in NIOSH. And a situation would be declared compliant if the risk of overexposure is below 30%, non-compliant if the risk of overexposure is above 30%. So that's the European guideline. So I had some slides about worst case, but I think I'll skip them for questions. It was just a recommendation that I found interesting. So maybe I'll take 1 minute to talk about this one for chronic toxicants. For me, it's a way of rendering worst case a bit more transparent and rigorous. If you want to use worst case, so the start of the procedure is there. It's in the book that if you find Modern Industrial Hygiene, a very interesting industrial hygiene monograph by Jimmy Perkins. So if exposure occurs in a restricted number of moments in a day. So here, Jimmy Perkins said, for example, less than 4 tasks a day and less than half an hour per task. If it's the case, then you might try worst case. And how do you perform worst case? Here, you take 4 task measurement. So you just measure during the task, not during the day. So this is like not assuming that your task lasts the whole day and not only during the task duration. So you take 4 measurements, and if these 4 measurements are below 1/10 of the DOEL, you don't need to go into statistics. So that's his way of saying, making sure that we really obtain worst case results. And then we can apply the worst case strategy. And if you can do that, you take the random sampling approach. So there's another one about acute toxicants. So there's not, what I would recommend you to do or anything. It's just, I think, a nice example of a pragmatic proposal to have some transparency and rigor considerations to apply the worst case approach. So my conclusion for this very short and partial summary of some recommendations. So they are all based on statistical inference. Most of them use screening steps to easily classify extreme situations one way or another without having to pay for monitoring and limit the cost. Overexposure is always defined as above 5% of exposure levels over the OEL, so over 10 days in a year, for example. And they are all, when you pass the screening steps, all the strategies require more than 5 samples. Yeah, so that's it. Thank you very much for your attention. So the last slides are correcting the question in your documents. And I'm here for a little bit if you have questions, of course.
Okay, thank you very much, Professor Jerome, for your presentation, and your presented material are very valuable. I think it is very useful for industrial hygienists, especially for our member in Indonesia. So thank you very much for today. I think we please all the participants give an online applause for Professor Jerome. Okay. All right. So thank you so much for tonight. We are very excited to meet you again tomorrow. So see you tomorrow morning for your time and tomorrow evening for Jakarta time. Thank you. See
Okay,
you.
well, thank you very much and enjoy the end of your evening, and thank you for sacrificing yet another evening for me. And
It is our pleasure. Thank you so much. Thank you. Have a good day. Bye-bye.
Thank you. Thank you. Bye.
Thank you so much, Prof. Jerome.
Thank you, Prof. Jerome.
Thank you.
Pramila.
Thank you.
Thank you.
See you tomorrow.